Cool. So I'm back again to go over one of the problems that somebody had requested, right? So this is one of the Chem 101 problems. I know that it's going to be due in like, what, 10 hours or something like that. But just even like looking at the Chem 101 thing, like the results of how many people were getting it correct or whatever, it definitely seems like a lot of people were struggling with this problem. So I'll just go over the approach, right? How to think about it and everything like that. So, reading the problem for hydrogen atoms, the wave function for the state n equals 3, L equals 0, and M sub L equals 0 is given below, where sigma is equal to R, which is the radius, over AO, and AO is the Bohr radius. What is one of the positions of the nodes, right? And so we have the wave function right here, right? And so there's a few different things to take into account, right? The only parts where R is present, right, are going to be the sigmas right here. In these cases, right, AO is just simply a constant. It's just simply the Bohr radius. And so if we break down a wave function, right, this part right here just simply describes, the amplitude of the wave, right? This right here then describes essentially the wave, right? Like what it looks like and everything like that. And as we can see, it slowly decreases over time. So, right, so this is the n equals 3, L equals 0, M sub L equals 0. So, what we can do is we can figure out this is the 3s orbital, right? So this is the 3s orbital. And so if we were to just simply draw it for ourselves, oh no. If we were to draw it for ourselves, right, just simply as something to think about, right, we know that essentially, right, you're going to have a node and then, right, it's going to look something like this right here, right? So there's two nodes that are present within the 3s orbital, right, within that wave and everything. And so the question then is, where is that position in these cases and stuff? And so, we can use this equation. And so to figure out the nodes, right, if we were to draw it out, right, so this is just simply the probability distribution, right, the way that it looks like for, where it's, the radial wave, right, versus, the radius, and then this right here is R, right down here, right, and this is R right here, and this is the probability, psi squared, right, this is just simply, right, psi essentially. Right, so if we look at that right there, right, there's 2 points, right, where the nodes are, and the nodes are when everything is equal to 0 in that case, right? So we can disregard this part of the wave function, right? The only thing that we really need to focus on is this part right here, right, of the wave function. So if we write that out, right, it's 27 minus 18 sigma plus 2 sigma squared, right? This is simply a quadratic equation, right? We can rewrite this as, right, 2 sigma squared minus 18 sigma plus 27. So all we have to do, right, is we can use the quadratic equation to get what the numbers are in these scenarios. Now, if you're not using a calculator or anything like that, right, the one method that's most straightforward, hopefully that you guys learned in geometry, is the factoring method, right? So we can sit down and we can factor it out. I already did that. I'm not going to go through that process right there. But essentially, right, what you pull out is that, right, and this is going to be equal to 0, right, because we're looking at the points where we're, the radial wave function, right, at position R, right, when that's equal to 0 in these cases. And so if we work our way out of that, right, what we get is, factoring it out, we get sigma minus 3 square root of 3 over 2 minus 9 halves. And then times minus sigma minus 3 square root over 3 over 2 plus 9 halves, right? So we get those two things that are factored out. So all we need to do now, right, to figure out what those positions are, right, when sigma essentially is equal to 0, is, we just simply now solve for sigma in both of these cases. So if we go right here, right, for this part right here, and we pull it out, right, what we get is negative sigma is equal to, here, actually, let me take a step back, right? We have 0 is equal to sigma minus 3 times the square root of 3 over 2 minus 9 halves, right? So we rearrange that. What we get is sigma, negative sigma is equal to negative 3 times the square root of 3 over 2 minus 9 halves, right? Sigma now is equal to 3 times the square root of 3 over 2 plus 9 half, right? Because we're multiplying by negative 1 in that case, right? So that way it's that. And because we're trying to figure out, right, where r is, right, in that case, we know that sigma is equal to r over that constant AO. So we have this right here. And so now if we rearrange this, what we get is essentially, right, r is going to be equal to 9 halves plus 3 times the square root of 3 over 2 AO in that scenario. One thing, right, is that for some reason Chem 101 didn't include the brackets around there, right, in those cases, right? So the AO, right, applies to both of those, right? Because it's just simply the units in this case, right? So we have this one right here. Right, and then if we solve for the other one, right, because there's 2 points where it's going to be equal to 0 for this wave function, right, we can do the same thing. So we have 0 is equal to negative sigma minus 3 times square root of 3 over 2 plus 9 halves. And so then what we get is sigma is equal to is equal to 9 halves minus 3 times square root of 3 over 2, right? That's equal to r over AO. And so then r is going to be equal to 9 halves minus 3 times square root of 3 over 2 times, AO over overall and everything like that. So those are the 2 points, right, of where it's going to be equal to 0, right, where one of the nodes is going to be located. Now, looking at this right here, right, what we can see is that this first one right here is 9 halves plus 3 times the square root of 3 over 2 AO, right, where it's all like this right here, right? So that matches this right here. So this one's correct. The next one is 9 halves plus 6 times the square root of 3 over 2, right? So that's not right. So if you did the factoring incorrectly, right, of the system, right, you're going to get that one wrong. 2, right, that's just not correct. I think the most common reason that people may pull that, right, is just simply looking at that number right there and using it, right? Same thing with 3, right? They may just pull it out and then just simply say, right, there's because of the 18 and stuff. And the 27, right? Both of those have, right, you can factor out 3s. The final one, right, looks pretty similar to the other one that we have, right? The other one that we have is 9 halves minus 3 times the square root of 3 over 2. The difference is, right, this is 9 halves minus the square root of 3 over 2, right? There's no 3. The 3 is missing. Right? And so that's why this one right here is then incorrect as well. So the only correct answer, right, is A. So the thing that you have to do for these types of problems where you're given the wave function and you're being asked to find the nodes, or at least draw the nodes and put down what the R value is you're going to have to use some of your knowledge back from geometry and factoring things out in those cases, right? Or, right, using the quadratic equation to solve for it. Because, right, that's how you're going to get the R values in these cases. So that's how you work your way through. This is, I think, problem 9 from this problem set 2 on Chem 101. But this way you can, think about how you approach that. And you can do the same thing, right, for all the other wave functions as well, right? Again, the thing that you really need to, focus on is just simply this equation right here. You don't care about the rest of the spinach, right? This right here is just the amplitude, right? This right here is just simply telling you what happens as, R, continues to go down, right? It just, essentially starts to taper off over time. But in terms of calculating where the nodes are, right, you just really need to only focus on that equation right there. So yeah, so that's how you approach the Chem 101 problem set 2, problem 9 in that case.